Okay. Yeah. So in the last few classes, we have been looking at band gap reference, and in the last class, we saw a brief glimpse into voltage regulator. So today, we'll look at some things about biasing. See, now you guys know how to make a band gap reference that generates a voltage that is independent of any variations in process voltage temperature. So in principle, you should be able to use this as a reference voltage and generate the required bias voltage for biasing your circuits. So that way the bias voltage will remain constant, right? So that is definitely something you could do. But it turns out in some cases or in many cases, let us say, you are not actually interested in keeping the bias voltage or the bias current constant, because you are more interested in some small signal performance from the transistors, right? From your circuit, you want some small signal performance. And for a transistor, what is one important small signal parameter that you are interested in? GM, right? So it makes sense that you want to have a particular GM in your circuit, right? Because as you know, I mean, GM determines the speed, GM by C determines the bandwidth, right? GM R naught determines DC gain, etc. So you want to keep the GM to be fairly constant. Now, if you keep the bias voltage or the bias current constant, that is nice, but that will not take into account the fact that you will have variations in threshold voltages and mobility. So although Vref is constant, because of these guys, GM will keep varying. So which means, let us say you change the temperature, the bias voltage or the gate voltage might remain constant for the transistor, but mobility and threshold will change. So do you think at high temperatures the GM will be smaller or larger? At high temperatures, what do you think might happen to mobility? I mean, remember, high temperatures meaning there is a lot of agitation. So which means, charge carriers will not be able to move slowly. I mean, it is like, if you have an empty hall, you can nicely move, but there are a lot of crowded people moving here and there, you will not be able to move fastly, right? Same thing. So mobility is going to degrade, so GM will reduce. So that's an issue. So there are ways in which you can have biasing such that the GM remains constant, and those kind of circuits are called constant GM bias circuits. So again, there are a whole lot of ways in which you can accomplish this. Let's look at one way today. And in many of these techniques, the underlying assumption is that the transistor obeys square law. Okay. Oops. Yeah. Because remember, we have to make GM to be constant, so we need to have some equation as starting point. So most of the circuits assume square law. So and in square law, GM is 2 times the drain current by the overdrive voltage, right? Now your goal is to keep this GM constant, right? Now think about it. I have some metric, some parameter that's going to change. I want to make this to be constant irrespective of any other changes in the system. What is the basic principle do you think I'll use here? I have something, I have to keep it constant. So what is the basic principle I'll use to keep this constant? Use some kind of negative feedback. That's all, right? So basically you, and for negative feedback, you take GM and you compare it with the reference GM, right? I mean, for keeping a voltage constant, you take a voltage, compare it with the reference voltage. Here you have a GM, and remember GM has units of conductance, right? So for reference, what do you think we should use? GM has units of conductance. So for reference, what do you think I should use? Some other reference conductance. So that's a resistor. We'll say we want it to be equal to 1 by R. And typically this can be an off-chip resistor that is nicely manufactured so that its value is constant. Okay. So yeah, so now the idea is you go and sense the GM of the transistor. If it is less than 1 by R, what do you do to the bias current? You increase it. If it is greater than 1 by R, you decrease it, and that's the basic negative feedback. Fine. And again, for comparing, we have to basically subtract the GMs. And typically, subtraction is much easier when done with currents. So I'll rewrite the same equation as ID. I want ID to be equal to the overdrive voltage by 2 times R. Right? The same thing. So let me probably call this as a reference current. So my job is to basically change my bias current here so that that becomes equal to the reference current. So, right. So now let's see how we can make a circuit for this. So obviously I need to have a transistor. So let's say this is my reference transistor. I want to pass in a current, bias current ID here, and change this current so that it becomes equal to this. That's what I have to do essentially, right? So for this I have to first generate the reference current. First step is to generate the gate to source voltage. Let me call it ID1 and VGS1. I'll call this M1. Yeah, let us say I pass a bias current through this transistor. Okay. Let me call this ID1. I obviously have to change it so that this current equals to this, right? And for generating this current, I first have to generate VGS1. How do you propose I generate the required gate to source voltage to sustain this current? Everyone knows, you basically go and do this. This will generate the required gate to source voltage to sustain the particular drain current. So let us say this is VGS1. So first part is done. So next I need to generate a voltage which is VGS minus VTH. Or let's start with a simpler case. Let us say I want to have VGS1 minus some voltage, I don't know, V hat, right? Now of course in principle if you have a voltage source like this you can go and put it, but of course you don't have. So you have to generate the voltage shift, and preferably I would want to generate it using a similar transistor so that things kind of track, right? So how do you propose I generate this level shifting using a transistor? Yeah, okay, so he stepped one, he jumped one step ahead. Let's take baby steps. So basically, if I have something like this, if this is VGS1, what will be this voltage if this is M2? Yeah, so if I call it VGS1 minus VGS2. Now of course, now I need to make this 10 to VTH. So how can I make it 10 to VTH? Yeah, remember, I want to have this VGS2 and I want this to be equal to VTH, right? And you very well know what is the overdrive voltage in terms of current? Under root 2 ID by what are nu COX W by L. So what can I change here to get, if VGS tends to VTH, what will happen to overdrive? So what can I do here to make overdrive 0? ID is something you can't change. Remember, I want to set ID to IREF. Huh? I can't change 2. I can't change this W, right? So what should I do to W? So ideally, if this were to be exactly equal to VTH, how much should the W be? Infinity. Let's start with infinity and then we'll do it. So in principle, if I have an infinitely wide transistor, I get this voltage, right? So now I have generated this voltage. Now how do I generate the current? I put a resistor 2R. So this is a reference resistor. Okay. So now the current flowing here is the required reference current, and that obviously flows here as well. So now I have generated the reference current. That's the step 1. Next I have to make sure that I go and compare my bias current with this reference current and change this guy so that these two currents become equal. Fine. So I have the reference current here. So to subtract this current, what should I do here? Remember, I have IREF. To subtract ID from IREF or vice versa, first I have to copy this ID here. So what do I do? Yeah, this has to be a PMOS current source. So if I do this, now this will be ID1. Now of course I can't keep it to be a constant current source because I have to change this, and as you can see here, if ID1 is not equal to Iref, what will happen to this voltage? That will change. So that can be used as a sensing point. If I call it, I don't know, Vp maybe. So if ID1 is greater than Iref, what happens to Vp? Increases. So as a corrective measure, what should I do? I should decrease ID1. How do I decrease ID1? If I call this the bias voltage, so I need to increase Vb. Now you see this increases, I need to increase this. Simple logic, I go and connect these two. Okay. Right. So if I do this, eventually the loop will settle so that the GM of this transistor will be equal to 1 by R. But this is nice, but let me make it more beautiful. So this will work, but do you think something that is practically not possible in this? Yeah, I mean this infinity should start to irk you. So of course I can't have an infinitely wide transistor, so let's see what we can do. Maybe I'll copy this portion. Right. So obviously I can't have it infinity, so let us say if this guy is sized at 1x, I make it m times wide. Now if this is not infinity, what changes now? Huh? No, I mean, why did we want this width to be infinity? Yeah, and why was that overdrive required to be 0? We want to get VGS minus VTH. Now if this is not infinity, this voltage will no longer be VGS minus VTH. Right? See, ideally you want this to be overdrive voltage by 2R. Now my width is not so large, so this voltage will increase or reduce. I mean earlier this was VTH. Now if I have a smaller width, this voltage will increase, so this will change. So this will no longer be V overdrive, it will be, let us say, some factor times V overdrive, right? So what can I do to get back the same reference current? I change the resistor, so I no longer use R2R, I use some value, some resistor Rx. That's all. Is that okay? So this we can quickly find. It's not that difficult. See here, if I write overdrive 1, it's square root of 2 ID by mu COX W by L. What about overdrive of second transistor? It's root 2 ID by. So can you tell me in terms of overdrive 1? It's going to be same thing, 2 ID by mu COX, right? So this will be. Okay. So now we can see what happens. The voltage here, I don't know what I can call it, maybe let me call this Vx. If I call that voltage Vx, this is VGS1 minus VGS2. I can write this as overdrive 1 minus overdrive 2. I'm just subtracting and adding a threshold so that this is. Okay. So this becomes V overdrive 1. Right. So the current that will flow through the resistor, so now this no longer must be equal to R, should be some Rx. So now the current flowing, if I call it Ix, that will be V overdrive 1 by Rx. This will be the current flowing. I want this to be equal to the reference current, which is this. So I just go and equate it. So from here you can find what is the required value of Rx, right? So let me write that. I'm making some space. So Rx will be what? 2R times, right? Now what do you think might be a simple value of m so that we get nice round numbers? If you choose m as 4, what do you get for Rx? Yeah, if I choose m as 4, my Rx will become R, and that's exactly what is done in practice. So you choose it to be 4x wider, which means this guy so if you do this now, the GM of these transistors will become exactly equal to 1 by R. So once that is done, you can take this and mirror it to any number of transistors, and all the transistors will have the appropriate bias current, so that the GMs of those transistors will also be equal to 1 by R, right? Because remember, as long as I bias it with a particular current, I am set. That current has been generated in the circuit, so I can take it and mirror it to any circuit you want and make GM of that circuit to be constant. Okay. Cool. So this is one common way in which this is done, but which one? Yeah, that's what this will typically be, an off-chip resistor. So you have very good zero temperature coefficient off-chip resistors, right? So yeah, this should be an off-chip resistor. Else you have to do something on chip so that this is a constant, right? Okay. So this is nice. This works, but let me copy. Yeah, but here we have ignored a lot of things. What are the non-idealities that can pop up now? Of course, channel length modulation. I mean, I assume this current is exactly mirrored here. That's not going to happen if you ignore channel length modulation, right? So let us say, yeah, CLM, nice abbreviation. Second, see, here I kind of did one step. The voltage Vx here is VGS1 minus VGS2. I wrote it as V overdrive 1 minus V overdrive 2. Yeah, so what did I inherently assume here? Threshold voltage of both transistors are same. Do you think that will be same? Yeah, remember the threshold voltage, unfortunately or fortunately, depends on the source to bulk voltage. The substrate or the bulk is typically grounded. So this guy has 0 source to bulk, but for this guy you have something. So obviously threshold voltages will not be equal. So you'll have body effect, right? So of course you can come up with techniques to make this better. Maybe you can see if you can. Yeah, let's say we'll try. See, let's start with channel modulation. Maybe I'll put it here. Okay. So remember the channel length modulation. I mean, what is the problem now? With channel length modulation, what is the problem? Yeah, why is that so? The drain voltages are not equal, right? That's the main issue. If I can somehow make these two voltages equal, we are set, right? And in our circuit, we connected the drain to the gate, right? Why did we do that? Yeah, remember, let's go back to the argument. This is VB, this is VP. We saw if, let us say, ID1 is greater than IREF, VP increases. Now to correct for this imbalance, I have to reduce ID1, which means I have to increase VB, right? So that is why we went ahead and directly connected it like this. But this will make sure that the two currents are equal, yes. But it doesn't guarantee that these two voltages are equal, right? So this feedback that we are using ensures the currents here to be equal, but it doesn't make sure that VP follows this voltage. So we can no longer use the simplistic feedback, should have a stronger feedback. So I should be sensing this voltage, and what should I do? I should compare it with this voltage and then tune this, right? If I go and connect it, this is basically, this will get set to some value to keep the two currents equal. But for me, in addition to making the two currents equal, I also need to make sure this voltage tracks this voltage, right? So which means I can no longer do the diode connection. What should I do? Basically I have to compare Vp. So let me use this. I have to compare these two voltages, and obviously that will be done using an op amp. So now tell me which is the plus and minus here, right side or left side? Yeah, why? Yeah, earlier we saw we were doing this connection, so which means if this increases, this should increase. So same thing, can do this. Again, here again you have both feedback in both the negative and positive terminals. You once again find the loop gain, you will find that if you do this, the negative feedback will be dominant. I'll give us an assignment, you can work out. Again, you break the loop here and then increase this voltage and see what happens to these two. It should act in such a way that finally the output reduces, right? Okay. So this will essentially take care of channel modulation and make it even better. Yeah, definitely can use. That will make it, I mean, it will not be as good as this, but it will be better. I mean, that's why I'm giving you the basic idea, right? You know what is the idea. Now we can make hundreds of circuits to do that, right? Now we can come up with your own circuits also. That's why I'm focusing on giving the fundamental idea. I'm not explaining the circuit, I'm explaining the principle, right? So the idea is you pump in some current here and make this current equal to reference. That's all. No, they are not current mirrors, right? Because see, for current mirror you need to have equal VGS. That's not happening here. The current mirroring is happening here. I mean, basically this we are doing it to generate the Vx minus Vth, whatever. This is VGS1 minus VGS2. To generate the reference current is why we are using this guy. Cool. So this is basically, yeah, this is one technique that can be used to take care of channel modulation. Let's also see if we can do something about body effect, right? For that I'll copy this once again. So again, let's understand what the issue is. Why is the body effect arising now? I mean, body is grounded. What is the issue? The source is not grounded. So if you were to avoid this, essentially I should keep the source voltages to be same. So let's say I take this guy here and the other transistor here. So let us say this is 1x and let's say it's infinitely. Let's say this is infinity, then we'll reduce it to 4. So now I don't want to have body effect. So which means these two potentials should be same. So let me call it VA maybe. This VB must be equal to VA. But if I do that, what can you say about the currents here? Will they be equal? No? Yes, no. I mean, look at the widths here, right? So basically I don't want to do this, so I'll keep it separate. We'll see what we'll do, right? So again, the first job is to, I mean, assume that we are biasing it with some current here, right? Some current is here, that's biasing it. Okay. This bias current is what we have to change. But before that, we'll generate the reference current. Let me write that here. That is VGS1 minus VTH by 2R. So let me push it here. Yeah. So tell me, I have this guy. Let us say there is a bias current flowing somewhere. That's fine. We'll come to it later. How do I generate VGS1? Again, to get the estimate of VGS, this is the only thing you can do. You make sure that you go and connect it. So what will be this voltage now? If this is VA, what is this voltage? VA plus VGS1. Right? Now remember, the source voltages here are kept equal. So I can't do the subtraction here like this, right? So let us say, which means I want to generate VTH. And remember, this gate to source voltage is VTH, right? So how do you think I can get an estimate of this voltage? Again, assume the current, there is some current flowing here. What can you do? I mean, remember, VTH is basically the gate to source voltage of this guy. The question boils down to the fact that I want to sense the VGS of this transistor. What do you do? Huh? You can diode connect this guy also. Now what is this voltage? That is also VA. I mean, that is VA plus VTH, right? So now think about it. I want to generate a current which is VGS1 minus VTH by 2R. I have these two voltages. What can I do to generate that current? Okay, that seems like the obvious solution. He's suggesting this. So if I put it to R, what is the current? Fine. But will this work? Huh? Why? I mean, if I do this, I mean, the water current enters here. Okay, that is true. But even before that, see, fundamentally speaking, who will provide the currents to your circuits? Huh? There should be a VDD, some voltage supply. So remember, the current has to flow from here, from the supply, right? So which means I should provide a path for the current to flow to the supply. So what can I do? I mean, the current, let us say, has to flow from the supply to here. Huh? Okay, no. I see, remember, I don't want to put a current source because this is the current I want to generate. This much is correct. At least some resistor should be put in between these two. But if I do this, there is no, this guy cannot provide the current, right? The current has to come from a supply VDD. The current has to flow this way. So what can I do? One simple thing. I'm saying this is the only path for the current to flow, right? So simpler thing is I connect this to VDD. Let's see. So what will happen now? This voltage is. So what will this voltage? Okay. So this is also this one. So this voltage I'll rewrite. This is VA plus VTH, which was VDD. So what is the current flowing? Same thing. I mean, it's nothing. Earlier you just had two relative potentials. The potential difference was the same. But the issue was there was no path from the supply. So I simply connected this guy to the supply that fixed this potential, which means other voltages will get set automatically. We'll come to that. We are still made that assumption, we'll have to do it, right? So this we can simplify it or basically redraw that by doing it here. Okay. Same thing. Resistor 2R is connected between these 2 points. So this is only half the job. So now what is the current flowing here? It is the reference current, right? Yeah, VGS minus VTH by 2R, that is the required reference current. Now here also we'll have the same current. I'll erase some of this. So here also I have the same current. Now I have to put a bias current here now and tune these two guys so that this current becomes equal to IREF. And at the same time, keep these two voltages to be equal. Two things need to happen. So what kind of current source I will use here? NMOS. Okay. Again, I have to tune this current by changing this, let us say VBN, to keep, let us say this is ID. I have copied this current here. Same thing, ID1 has to be made equal to IREF, but in addition I also have to make these two to be equal. So what do you do? The same thing we saw some time back. So let me make some space for the op amp. Okay, broken its mouth. So you sense these two. Right. So what do you think will be the signs? Which side will be plus? Right side, because again you see if this current is greater than ID, I have to increase ID, which means this voltage has to increase. So I basically have to follow this. So this will be plus and minus. So once again, by working out the loop gains, you can prove that this is still in negative feedback. Okay, maybe actually there is one other thing. Let's see if we can make that circuit. Yeah, so this is one way in which you can avoid body effect. Again, now it's instead of infinity, I'll use 4xy transistor and use R. Same thing as before. Okay. So yeah, there is another thing that you can do. Let's see if we can do that. This is the whole circuit. Again, the goal is to make sure there is no body effect between the, mismatch in threshold voltages for the two NMOS. So once again, you can start with this. I have the left side M1 here, sorry, M2 here. So I have to keep the source voltages to be same. What is one trivial potential I can connect the source to? I can also connect it to ground, right? I mean, this is fine. Right. Again, assume that drain current ID1 is flowing in the transistor. So again, the job is same. I need to generate this voltage. So first I'll do diode connection. Let's say I make nice diode connection like this. So this is VGS1. And as usual, if I have infinitely wide transistor here and pass a current, this will be VTH1 ideally. So now the job is, I have VGS1 here, right? I need to generate VGS1 minus VTH by 2R, right? So where do you think I can connect the resistor? I mean, if I do this, first of all, this does not work because it doesn't generate the gate voltage. Second, there is no path for the current to flow through the gate. So basically, although this looks a simple choice, but we can't put it because putting a resistor to the gates will not make any current flow. So I can't connect the resistor to the gate. So where else I can connect the resistor here? See, the point is, it is clear that VGS1 is the terminal to which I have to connect the resistor. At least one point should be VGS1, right? So tell me where else I can put the resistor? Yeah, a simpler thing, I mean, you can use buffer and all, but simpler thing is to actually go and put resistor here. Hold on, so now I want to keep this equal to VTH. What can I do? I already have generated the, if I have an infinitely wide transistor, right? I can basically connect this. Okay. So now you see, we'll put the same guy here. So which means the currents in these two branches will be same. So we have some current flowing that will generate the required gate voltage here, and that will obviously be equal to this. Another thing you can do. Okay. Cool. So yeah, Again, this is not the only way. You can think and come up with your own circuits. Now I just want to mention something. Yeah, VD, I mean, here also VD would not be same. I mean, which case? Yeah. So which means you can put an op amp and do this, right? I mean, I've just redrawn the NMOS section. The PMOS section will, the same thing will come here. So you can put the op amp and so I just want to discuss one slight nuance about this guy. See, as I mentioned, let me erase all this. Not needed, not needed, not needed, not needed, not needed. So this resistor is a reference resistor, and that's typically off-chip resistor because you want to have a nicely controlled resistor value, right? So which means this will be basically connected to your pad on chip, and from there externally you will put the resistor. Okay. So which means here obviously there is going to be a parasitic capacitor. Let's call it CP, right? And even if not, I mean, one typical thing that IC designers do is this. See, if you have some bias voltage generated on chip, it is a DC bias voltage. You don't want it to change, right? So to prevent any fluctuations in this voltage, what do you think we can put here? Yeah, filter, basically what's the simplest? It's a DC filter, a capacitor, right? There are multiple ways in which you can interpret it. This is to ground, right? So this capacitor basically, I mean, if there is any disturbance here, the capacitor will provide a low impedance path, so nothing changes. In other words, I mean, also if let us say this whatever thing you're connecting here, that draws a lot of high frequency currents, that need not be provided by VB, the capacitor will provide, right? That's because the moment you put a capacitor, it gets charged to VB, so it is now acting like a voltage source, right? So this is typically something that is typically done on chip for making sure all DC potentials are remaining fairly constant. Else otherwise there can be some stray coupling from somewhere that can momentarily change or reduce or increase it. So to keep it fairly constant, this is something that is done. Now sometimes people also tend to put a explicit capacitor here because this is also supposed to be a DC potential, right? So let us say you put that, and total cap I call it CP, right? So let us say you put a large cap here. So do you think, do you foresee any issues here, or things will be fine? Okay, or for that first, I don't know if you recognize it. See, let us say, let's not even consider capacitor now, let's look at DC picture, right? So what kind of feedback do you think we have here? We have positive feedback. This is something we saw during, when we discussed band gap also, because let us say, I increase this. If I increase it, what happens to this voltage? This decreases. What will happen to this voltage? You have positive feedback, but why does it work? The magnitude of the positive feedback loop gain was less than 1. Again, the other way to interpret is, in addition to the positive feedback, do we also have something that is giving negative feedback? This source regeneration was providing negative feedback, and in fact if you compute the loop gain here, let's compute it, right? So I apply a test voltage and see what returns back. So what will be the incremental current here? I have, ignore R0, I am applying a test voltage Vt to the gate. I have a source regeneration. What is the small signal current? Again, simplest thing is to find this voltage. What is this voltage first? GMR by 1 plus GMR. So the current is divided by R, so that's basically 1 plus GMR times V test. So this current is I, the same current is mirrored here. So what will be this voltage? This is the return voltage. What is that? I mean, if this is I, what is this voltage? I mean, you have a current type getting pumped into this node. What is the resistance here? What is the voltage? I by Gm. So if I do this, what do you get? Right. So that's why the positive feedback loop gain was less than 1, right? And as you see, this negative feedback here is what is kind of reducing the loop gain's magnitude to be less than 1, right? So that is other way to argue. You can say although you have positive feedback, you have some negative feedback getting provided by the source degeneration, and that's bringing the magnitude of the positive feedback loop gain to be smaller than 1, right? So with that understanding, let me put here, let me erase all the unnecessary stuff here. So now tell me, if I put a large capacitor here, do you foresee any issues? High frequencies, what happens? Yeah, at high frequency, if you put a very large capacitor, even at relatively small frequencies, this will be a short. So you are losing this guy completely. So which means the magnitude of the loop gain in positive feedback can become greater than 1. Okay, and in fact now we can go and compute. So let us say I break the loop here and try to find the poles and zeros. Let's do that as an exercise. So I'll have parasitic capacitors, say from here, that's all. So let's call this C1, C2 maybe. This is the input where I apply the test signal. I check the return signal here. So what is the loop gain at DC? We just saw it's 1 by 1 plus GMR. This is fine. How many poles do you think we'll have here? 3 poles. I mean, all 3 capacitors, you can set their voltages independently. No worries. And let's ignore R0 for every transistor. That makes life simpler. So what do you think is the pole contributed by this guy, if I call it P1? I mean, look at the total impedance here. I mean, capacitance is C. What is the total impedance? R parallel 1 by Gm, right? See, once again here, because I have ignored R0, there is no coupling between these two guys. So you can treat everything as an uncoupled RC section. So the poles are approximately the conductance by the capacitance, right? That's because I've ignored R0 everywhere. Okay. So which means, see, yeah, here as you told, the resistance was 1 by, let us say, Gm2 parallel R times Cp. So if I simplify it, I think we'll get 1 plus Gm2R. Okay. Yeah, I think that's what we'll get. So what about the pole due to this guy, C1? What is the impedance here? You just have diode connected PMOS here. Okay. The impedance is 1 by Gm. So what is the pole? Let's say Gm of the PMOS by C1. And what is the third pole? Third pole due to this guy. I mean, here the total impedance is only this fellow, right? Gm of the NMOS, Gm1 by C2. Looking down, I mean, we have ignored the output resistance of R0, right? Yeah, if R0 is there, that becomes, 1 by Gm parallel cascode impedance. But again, that will not be very tricky because this will now be coupled. It depends on whether the CP is providing a low impedance or a high impedance, right? Basically, if CP is contributing to the low frequency pole, then you should treat it as a short and find the impedance. So to avoid all confusions, I ignored R0. So there is no coupling. Just treat each of them as independent RC sections and do it. So these are the poles. Do you think there is a 0 here? Let's say I short the output cap. What happens to VR? 0. If I short this guy, what happens? If I short this guy, what is the input to this transistor? What will be the current here? No, I mean, if I short the gate, incrementally, the gate is also ground, source is also ground. Current is 0, this voltage will be. So these two capacitors cannot be shorted. What about this cap? I can still short it, I'll get some current here, right? So the 0 will be contributed by this guy, and you can actually quickly find it. Okay, the way I've computed. Okay, so we'll assume as usual. Should I copy it? It's okay. Let's say this is 0 output. So this is 0. So if you apply KCL at this node, we have GM VGS of this transistor plus GM VGS of this transistor, both of them adding to be 0. Let me write it maybe. GM of the M1 times VGS plus GM of the PMOS times VGS. Fine. For the NMOS, already gate is ground, source is ground. So this is 0. What can you say about PMOS? No, from this, what do you infer? Yeah, VGS of the PMOS also must be 0. Source is incrementally ground, which means, fine. So this is 0. So now you try to apply KCL here. So you already know GM VGS from the PMOS is 0, right? This guy is there. So what is this GM? Let us say I call this Vx. GM1 should be 0. So what does it mean? Vx is equal to Vt. So now you apply KCL here. So if you apply KCL here, what do you get? I mean, the current GM1 into Vt minus Vx should be equal to Vt into Vt by R, and I already know this current is 0. So right. So where is the 0 located now? Okay. I mean, just another example. Again, the idea is you start by considering the output in the Laplace domain to be 0. You try to apply KCL and you will get it finally. So these are the poles and zeros. Let me copy it freshly. Maybe hold on. This is the circuit. So I don't need the circuit. Let's say. We have an additional 0 at 1 by RCP. Okay. So let's quickly check how the loop gains magnitude plot look like. Right, omega versus at DC it is something very small. So let us say somewhere here it's below 0 dB, but it's not very clear. But let's say this is the DC. Right. So which of them will come first? Do you think? I have this guy. These two guys, which do you think will occur first? I mean, let's assume this capacitor is going to be large because you have a large parasitic capacitor at the pad. Plus, let us say you go and additionally put a capacitor to keep that voltage constant. So CP is going to be very large, right? So which means one of these two is going to occur first. Of these two, which will occur first? 0 will occur first, right? So I'll have 0 first. So which means what will happen to the magnitude? Increase. And then what will come? This guy will come. So that will flatten it out. And after some time, P2 or P3, whichever comes. So now you can clearly see if the capacitor's values are in such a way, the capacitor's value can be in such a way that this can actually cross 0 dB. Okay. So the magnitude of the loop gain at some frequency can easily become greater than 1 and things will become unstable. So if this is the case, let us say you are not putting an extra capacitor in CP. CP is an existing parasitic capacitor and you see that this is happening. What is the fix? How do you add a pole? I mean, I already have these two poles. See, remember, the pole 1 and the 0 are kind of a doublet, right? basically, yeah, 0 and pole, they kind of follow each other. So this is something you can't prevent. Basically 0 Z1 followed by P1 is something you can't avoid. So what you should do now? Should bring P2 or P3 further in, right? Sorry? But 0 will always come before that, right? Because you see, this is 0, this is pole. The first pole and 0, they are kind of close by. You can't change one without affecting the other. So the only solution is, as you guys pointed out, you have to bring, let's say, P2 or P3 in. So essentially, you have P2 here, so it drops, and then the 0 comes, flattens it, and then the pole comes, and then. So you can bring either of P2 or P3 closer. So how would you do that? I mean, instead of decreasing GM, simpler thing. I can add a large capacitor, right? So you have to put a even larger capacitor that dominates CP on. Let me take it to the next page. So you have to put an even large capacitor on either of these two nodes, right? Only then you can actually get it. And this is something typically people might tend to overlook, right? I mean, in fact, this happened to one of my friends. He designed a chip, and this was a biasing circuit, and he had an off-chip resistor. And as a very careful designer, he put a large bypass capacitor on chip. Nothing worked. The entire chip didn't work, obviously. Biasing was not fine. And then he, for some few days, he was stuck. He didn't know what was happening. And then randomly, when we were discussing, we came to know about this. And then once he desoldered the extra cap he put, the chip worked like a charm. Right? So essentially, this is something people can tend to overlook, because you think that this is a DC biasing circuit. I'll just check the DC operating point. It's working. It's good. But remember that there is a positive feedback loop here. So whenever you have such positive feedback loops, you should also run a stability analysis here and make sure that it is stable. That is, the loop gain of the positive feedback should not exceed 0 dB at any frequency. Okay.
So what we want those disturbance so that positive feedback becomes efficient?
I mean, there can be any noise in the circuit, right? I mean, there is always noise in the circuit, right? So essentially, if there is any kind of current injected in the supply or somewhere, that's going to kind of blow. Finally, the other thing is, you can also have a case. See, typically you will not connect the supply all the time, right? The circuit is going to be off and you power it on. So which means the VDD is not a constant, it is a step. That is enough excitation for this positive feedback loop to kick in. Right? And the other minor point I want to make is, so this circuit also, if I copy this once again, see here also, if you actually try to solve it, you will find that this has an operating point where all the currents can be at 0 and things will be fine. Okay. So these kind of cell bias circuits have this issue that if you don't take care of it, there is a possibility that the circuit will be dead. That is, all the bias currents will be 0. So the voltages will be at 0 or VDD, whatever. So for this also, you need to have what is called a startup circuit that senses if the circuit is in this all 0 operating point condition and then pushes some current. For example, let us say this voltage is 0. So, I mean, basically this current is 0. You can have a small circuit that pumps in a small current initially. So once current is going in the transistor, this voltage will develop and the positive feedback loop will kick in and establish all the voltages appropriately. And once the circuit is fine, this should not pump in any current, right? You can come up with multiple circuits. So that is one thing. So yeah, that's about this. And one thing I wanted to mention about the problem. This is something about the problem set. So I don't know if you guys noticed. Do you guys remember solving this one? Okay, I'm sure no one did. Did anyone remember solving this or no one solved? I mean, the question is here, I want you to find the noise only due to M1. Right? So let me see. So if you find it, let's see what you get, right? I mean, let's say Vn is 0. I mean, for M1's noise, I can either model it using a noise current or the noise voltage. If I do using a noise current, you see the current is floating. You have to break it into two grounded current sources and put in series like this. Something. So instead of that, a simpler thing would be to take a voltage source. So let us say this is Vn1. Right? So tell me what will be V1 due to Vn1. So if I redraw the circuit, I have Rd. That's what I have with respect to M1, right? So what do you think will be the drain voltage V1? Yeah, I mean, so first of all, I mean, you guys know what is the incremental current here, right? What is it? I mean, that's very approximately, but can it be more? Gm by 1 plus Gm Rs times Vn1. So what is V1? Minus of this current times Rd, right? So it's minus Gm1 Rd by 1 plus Gm1 Rs. Fine. Let me erase it. So what is this voltage? If I call it Vx. Yeah, you guys know it's Gm Rs by 1 plus Gm Rs. And why am I finding that voltage now? Yeah, this voltage times the intrinsic gain of this is V2. So what is V2? It's minus Gm2 into Rd times Gm1 Rs by 1 plus Gm1 Rs. Right? Now my output is V1 minus V2. So what do you get? And let's assume GMs are all equal for simplicity. Maybe that will simplify it. So let's say it's Gm Rd times, right? Right? I mean, for simplicity, I've assumed GMs are equal. Right? So what do you observe now? Sorry, thanks. Right? So is there something interesting happening? It's not interesting to you. I mean, what I have found here, it is the contribution of the transistors M1's noise to my final output V1 minus V2. That seems to be having a term which is Gm Rd by 1 plus Gm Rs times 1 minus Gm Rs. So is there something I can do here to reduce the noise contribution? Yeah. If I make Gm Rs to be equal to 1, what can you say about M1's noise contribution? It doesn't come. Right? So that will make, this is due to, so what's happening here is what we call as noise cancellation. See, one thing to notice, when you're cancelling noise, you should make sure that the input doesn't get cancelled, right? I mean, remember, your noise is adding with your input. When you're attempting to cancel noise, if your input is cancelled, I mean, there is no point, right? So you can verify if what's happening to the input also. So let's say I have V in here. So let's just look at the signs of the signals here, right? So if I apply V in here, V1 do you think will be some plus V in or minus V in? I mean, what I'm asking is, see, here I'm applying the input here. It's connected finally to the source, and then that's processed and you get it at the drain. So do you think V1 will be plus V in times some gain or minus V in times plus V in? Okay. So what do you think will happen to V2? Minus V in times some gain. So if you take the difference, input is kind of getting added, right? So input is getting added, but the noise is getting cancelled. And if you actually think about why that's happening, here if you see here, maybe see if I look at the input alone, as we saw here, if this is plus, this is going to be plus, this is going to be plus, this will be minus. But if you look at noise, if this is plus, what will happen here? V1 will be minus, so here it will be plus, right? I mean, I am applying at the gate, source will follow with the same polarity, and here it will be. So essentially have created a path wherein the signals kind of add, right? So basically if you look at V in, you should have two nodes in your circuit. In node 1, I should have, let us say, plus V in plus some noise. You should have minus V in plus noise, or vice versa. So as long as if you can create some two different parts in your circuit, that happens in such a way that for signal there is a sign inversion, but for noise it is not, or vice versa, then you can actually subtract it and get rid of noise. So this is a general principle in noise cancellation. So now you can think and see if you can come up with better circuits, right? Cool. So I'll stop here. I exceeded time already.